How do you check if a function is uniformly continuous? One way is to use the definition we talked about in our last video in this series. However, there are lots of beautiful theorems that tell us sufficient conditions for a function to be uniformly continuous. One of the most important conditions is the fact that any function that is continuous on a closed interval is actually going to be uniformly continuous. And if you have a function, like for instance this one here, that's only defined when x is non-zero, right, because we're dividing by x in the formula, such a function is going to be uniformly continuous if and only if we can extend that function to be continuous on a closed interval, which includes its inputs. And so this graph here, there's no way that I can define this at 0 in a way that's going to make it continuous, because the points very near 0 are taking on basically every value between 1 and -1. So this function is going to be no. On the other hand, any function that is continuous on a closed interval, for instance this one here, is automatically going to be uniformly continuous. And in the last video I talked about this function here, and I talked about how in practice we could find that delta by looking at the steepest part of the graph. In general, if you know that your function has bounded slope on some interval, and that there's some point that has the steepest slope, well, as an exercise maybe in the comments, there's actually a way to define delta in terms of epsilon and that steepest part of the graph. This is because functions with bounded slope, and here I'm talking about slope not of tangent lines, but between any 2 points, so secant lines, those functions are called Lipschitz functions, and Lipschitz functions are always uniformly continuous on their domains. My students will be proving that for their homework this week. I'm very excited to read their proofs. And so using this short list of rules actually gives us a great way to check whether a lot of functions are uniformly continuous. For instance, even though this function isn't currently defined at 0, I can add a point in at 0, namely the point 0, 0, and I will get a function that is continuous. And since we're now defined on a closed interval, say from 0 to 1, we will have uniform continuity. Another important property that any uniformly continuous function will have is that on a bounded interval, for instance on the open interval from 0 to 10, the function itself has to be bounded. It can't go off to infinity. This is one way to see, for instance, that the function 1 over x in our last video is not uniformly continuous on the open interval from 0 to 10. And by the way, the proofs of these things don't use techniques that we haven't seen so far in this proof. For instance, to prove that a function that's continuous on a closed interval is uniformly continuous, we just do a basic proof by contradiction, keeping track of how epsilons and deltas are working together. We'll even use the Bolzano-Weierstrass theorem at some point. But lurking behind the connection where we fill in the endpoints to go from an open interval to a closed interval in a continuous way, there is actually something about Cauchy sequences that I'll talk about in the next video.